Okay, so imagine a material that can remember its original shape, and with just the right signal, it can transform right back to it on command. Now, I know that sounds like something straight out of science fiction, but it's not. It's a real revolutionary technology that's happening right now. Let's break it down.
So to really get a handle on this new tech, we've got to look at where the idea came from. And when it comes to materials that can respond to their environment, nature has always been the ultimate engineer. I mean, just think about the Venus flytrap, right? It snaps shut in less than 100 milliseconds the second an insect touches its little trigger hairs. That incredible, lightning-fast movement got scientists thinking, what if we could create materials that do the exact same thing? And that inspiration, it led to the very first generation of these man-made smart materials, shape memory polymers, or SMPs for short. They are the foundation for everything we're about to talk about. So at their core, SMPs are basically polymers with a kind of built-in memory. You can bend them, twist them, lock them into a totally new temporary shape. But then, with the right trigger, and usually that trigger is heat, they just snap right back to the original shape they were programmed with. The whole process works in this simple three-step cycle. First, you've got programming. You heat the material up to make it soft, and then you deform it. Second, you fix it. You just cool it down while it's in that new shape, and that locks it in place. And finally, recovery. You apply heat one more time, and that triggers the memory, causing it to spring right back to its permanent form. So how does it actually work? Well, the secret is all in its molecular architecture. The best way to think about it is like this. You have a stable, permanent skeleton that never forgets the original shape. Those are the net points. And then you have these flexible muscles that can be locked into a temporary position. Those are the switching segments. When you apply heat, it basically loosens up those muscles, and that allows the skeleton to pull everything back into its original form. Pretty clever, right? But while this first generation of SMPs was definitely clever, it came with some pretty big drawbacks. And those drawbacks really held it back from being used in more demanding real-world applications. For one, these early polymers just weren't very strong. They couldn't really perform much mechanical work, and their shape recovery was, well, slow. On top of that, they almost always needed an external heat source, like a heat gun or something, and that's just clumsy, it's imprecise, and honestly, it's totally impractical for a lot of situations. So this created a really clear gap. The reality of these basic SMPs was, low strength and clunky direct heat control. The dream was a material that was strong, super fast, and could be activated remotely with precision. The challenge was obvious. How in the world do we bridge that gap? And the answer, as is so often the case in modern science, came from the world of the incredibly small. The solution was nanotechnology. Basically, adding tiny functional particles into the polymer to give it some serious superpowers. And this creates a whole new class of material, the shape memory polymer nanocomposite. You can think of it as a hybrid that combines the memory of the polymer with the really powerful properties of these tiny nanofillers that are embedded inside. And these tiny additions are a total game changer. They act like microscopic reinforcements, which solves the strength problem. They also improve how well the material conducts heat and electricity, which solves the speed problem. But most exciting of all, they unlock completely new ways to trigger the material, which solves the control problem. And this brings us to a whole new toolkit of triggers, which lets us control these materials remotely and with just incredible precision. Okay, for example, what do you think happens when you mix in some teeny tiny magnetic particles of iron oxide? You get contactless control. An external magnetic field makes those little iron particles heat up from inside the material itself. This internal heating is what triggers this shape change, and it allows something like this gripper to work without any wires or any physical contact at all. Okay, that's cool. Now, what if we use gold nanoparticles instead? Gold is known to interact with light in a really interesting way. Now you've got a material that actually responds to specific colors of light. By embedding different shapes of these gold particles, you can trigger different parts of the device just by changing the color of the light you're shining on it. I mean, look at this actuator. One color makes it bend down, another makes it bend up. That is an incredible level of precision. And for one last example, what if we weave a conductive little network of carbon nanotubes all throughout the polymer? Well, you basically create a material that has its own internal wiring. You pass a small electric current through it, and the nanotubes heat up instantly. It's a process called Joule heating. This is one of the absolute fastest ways to trigger the shape change, giving you that almost immediate response that you can see happening in these thermal images. So this is way more than just a lab curiosity. This combination of shape memory and these nanotriggers, it's really the foundation for the entire next wave of smart technology. And this right here brings all the pieces together. In the middle, you've got the core materials, these nanocomposites. Then, surrounding them, you have the triggers we talked about, like heat and light. And those, in turn, enable this huge range of applications that are branching out into things like robotics, biomedical devices, and flexible electronics. And the potential applications here are truly mind-blowing. We're talking about things like medical stents that can expand perfectly inside a blood vessel triggered from outside the body, or soft robots with artificial muscles that move without any bulky motors, and even flexible electronics that can literally fold themselves up for storage and then unfold when you need to use them.
This all really points to a fundamental shift in how we think about building things. We are moving away from building with passive, static materials to designing with dynamic, programmable matter. The materials themselves are becoming the machines, which leaves us with one really big question to think about. When our materials become programmable, what will we build next?